Здравствуйте.
Hello.
Yeah, hello everyone. Let's wait for 1-2 minutes and start. I'm kind of more or less ready. Okay, it works. Okay, so I think let's start. Oh, wait, I haven't input the code. Okay, now the demonstration should work. Okay, fine. Okay. So let me say that your tests, I haven't finished checking yet, unfortunately, I'm sorry, but I'm almost finished. I hope to finish tomorrow. And if it goes wrong, then it will be the day after tomorrow. Well, I think there is nothing to discuss there anymore. But let me also say that the part that I've checked, the results are very good and I'm quite happy, etc., etc. But of course, that doesn't mean you can slack, because the next text is harder and the next is even harder, and so on and so on.
Where would this upper than 8?
Well, I don't know, because I've checked them not horizontally but vertically. I mean, I've checked the first 4 problems in all works. Well, more than the first 4 problems, but the first 4 in every work. And so I don't know the total marks at all. But I know that almost everyone is higher than 4, which is good. And many of you are higher than 6, which is also good. But I don't know exact marks yet. So that being said, let's go to complex numbers. If there are any questions, please do ask right now. Otherwise, we shall start. Okay, so last time we talked about complex numbers using their algebraic form, the form a plus bi. However, it so happens that complex numbers can be represented in yet another different form, and it will help us to solve problems. The idea is as follows. Suppose one has a complex number z that equals a plus bi. Then one may draw a picture of this complex number by picking a point on a plane with coordinates AB. This is a simple way to make pictures for every complex number. Then one may consider this vector from this beginning of the coordinates to this point. This vector can be used instead of the point. This is kind of a very often made move. In algebra, we think that vectors are kind of more nice to deal with than points, so we prefer them. But they're interchangeable. Such a point is the same as this vector, and this vector is the same as this point. But if you consider it, now you may how to say, I forgot the word.
Perpendicular.
Perpendicular is called altitude in this context, but I forgot the verb, how to say провести.
Draw. Drop.
Find.
What?
Find.
No, find is descent,
Line,
but not
line.
really. And draw is bad. And what?
Line.
No.
Okay.
Okay, there was some proper verb for this, but okay, let's forget this part. Still, we can draw an altitude like this. And so here, this becomes a right triangle. And its legs, their length is A and B respectively. And we may compute the length of the hypotenuse as follows. Using Pythagoras theorem, I hope everyone knows it. And so this length is called the absolute value of a complex number. And in Russian, that is модуль комплексного числа. The same way as with real numbers, they have absolute value. The same way we have absolute value for complex numbers, where the sign of the square root means the usual square root. The reason why I say so is because in the end of today's seminar, we will have some unusual roots, but this root is the usual square root. Okay. The number under the root is non-negative automatically, so this root is always, we are always able to take it. There are no hardships, no problems. Okay. So using this absolute value, I may rewrite my number as follows. Okay. This way it becomes more strange and less nice, but I claim this will help us later, so let's deal with it for a moment. So now, well, this part is outside of the brackets. Let's focus on what happens inside of the brackets. So here we have two numbers, this number and this number. And I claim that they are automatically between -1 and +1. I won't prove this right now, but that's kind of very easy to prove using some inequalities. Really easy stuff. So also the sum of their squares is very easy to compute. If you compute it, everything cancels and you get 1. So those three properties, when they are satisfied for a pair of numbers, it automatically means that in fact, those numbers are a cosine and sine of some angle. So this means I can rewrite my number z in the following form. The number outside of the brackets remains, and the thing inside becomes cosine of phi plus I times sine of phi, where phi is some angle. So this form is called the trigonometric form of a complex number. Or also it is called polar form. Please note that such phi can be found from those two equations, but not uniquely. Because if I change phi by 2 pi, for example, if I consider phi plus 2 pi, then the cosine is the same and the sine is also the same. This is a well-known formula, I hope. Thus, this angle will provide the same results as this angle. So in practice, we can use either of them and of many other options. I can consider the set phi, phi plus 2 pi, phi plus 4 pi, phi plus 6 pi, etc., infinite set, and here phi minus 2 pi, etc. Okay, such a huge set of different angles, and all of them have kind of the same meaning for me. This set is denoted as argument of z. It is called argument and denoted like this with capital letter A. This capital letter is meant to somehow mean that we have not one number, but infinitely many of them. And sometimes, well, we want to denote one particular number of them. It's not nice to have infinitely many numbers. Then we write argument of z with small letter a. This is the number from here such that it belongs to this interval. From out of all of those numbers, one of them belongs to the semi-interval 0 to pi. Also, in some books, please note that in some books they use another interval, this one. But as far as I know, well, I asked the other group, lecturer uses this one. It doesn't really matter. It is a matter of convenience. Okay, so any questions for the theoretic part, or we go to problems? Fine, let's start. So, I'm sorry, something doesn't work. Okay, it worked. Very good. Now it doesn't. Yeah.
What is a written argument Z is equal, and this first element is just -1 should be,
No,
or
I'm sorry. No, it's my bad script. It is etc.
I see.
5 minus 4 pi, 6 pi, etc. Infinitely many.
I
Okay.
see.
Okay, thank you. So, yeah, people told me that my script on this board will become better and better with practice, but I don't know, we have like 2 years of practice already and it doesn't help. I'm sorry. Please ask me immediately if I write something unclear. So we have a number here, number 5, that is a complex number 5 plus 0i. Well, if it is a complex number, it has a trigonometric form. The question is how to find it. This is an open question. Aha, no one knows. Wait, that can't happen. We've just discussed that we need to find the absolute value in the argument. So what is the absolute value of 5?
Is 5? Is modulo 5?
5.
Well,
Square root of 5 squared plus 0 squared.
yeah, that's better because, well, you're right, that is indeed 5, but I wanted like the procedure to find it. So by examining this procedure, you see that indeed the result is the same as the usual absolute value. That's good. It would be not convenient if this meant something else than 5, but lucky for us, it doesn't. So, okay, we have to take this absolute value and put it outside of the brackets. And in the brackets, what remains is 1 plus 0i. Now, I have the following system. Cosine of some angle equals 1 and sine of the same angle equals 0. Are we able to find this angle? I wonder.
I know in the usual properties with the cosine and sine, just the usual trigonometric solution. So the phi should be this
E?
0, 0, 0.
0 is good.
But this is
But
2 pi plus k.
yeah, that's much better. Thank you. This is the series of solutions, infinitely many solutions. Okay. All of them satisfy those equations and nothing else satisfies. So in my particular problem, for convenience, I pick one of those. So this set is the argument with capital A. I pick one particular argument, and using it, I may write my number like this. One small note, which is not important at all, but just so that well, to say it explicitly, when we write the numbers in algebraic form, I usually put I after the number. That's, well, traditional, okay? Like we put X after the coefficient. We discussed it last time. But when I write trigonometric form, the custom is to write I before. Because if I write it after, it is not clear. Is it inside of the sign or outside? Okay.
Okay.
It's just a custom. It doesn't really have any explanations. Well, it does. I have just provided the explanation, but it's not something very important. Okay. Are there any questions for this part before I go to the next one?
I have a question. It means that so any number we can write trigonometric form in this system, yes?
Yes, for any number, I can find the trigonometric form using such a process, and we will do it in a few moments with several other numbers.
Okay.
So here is another example of the number I, which is 0 plus 1 times I. What is the absolute value? Now we don't have any intuition. Now we don't know what is it, but we are able to find it.
1.
Indeed, it is square root of this, which is 1. So I put 1 outside of the brackets and inside, well, nothing changed. So I'm looking for an angle such that its cosine is 0 and its sine is 1.
P
This is
divided by 2.
P divided by 2.
Pi
This is
over 2
pi over 2.
or pi divided by 2, that's synonyms, okay? Plus,
Yes. Plus k. Where's
plus
k?
k. No.
But we have
2 pi k.
but here's 2 pi k. I just mean, sorry.
Okay, so pi over 2 is like the main part, the interesting part, and this plus 2 pi k is like, well, that's life, this happens. So I can again consider a particular value and write that I equals cosine of pi over 2 plus I sine of pi over 2. Please note that this notation is kind of slightly longer than this one, okay? That's life. That's a disadvantage of this form. However, I claim again, it will help us to do some computations soon. So it's not useless. We will see in a few moments. Any questions for this part? Or I go further?
I'm not sure how we get this module I. This
Module.
is how we-
So again, I take the square of this coefficient plus the square of this coefficient and take the square root.
I see. So we just like imagine an algebraic form.
Yeah.
And then just like a 0 is this instead of an integer real part.
Well, it is that it is integer. That's a coincidence. It could be some square
Not
root.
the
Or
integer,
something.
but like
Yeah.
a real
But
part.
this is, yes, the real part, and this is
I
the
mean,
imaginary part.
Yes.
Very good. Let's move on. I have one more example of the easy kind, -2. So we have to find its absolute value. And well, it's kind of obvious that once again, it is the same as the usual absolute value. So that's 2. So now minus happens inside of the brackets. So we have the following system. And again, it's easy to solve. I will immediately write the answer, not waiting for you, because that's well, one another exercise of the same form. So I can pick one particular value from this, well, pi, for example, and write that -2 equals this. Please note that this has geometric meaning. -2 is some, if 1 is here, then -2 is somewhere here, and this angle is pi. So 2 is the length of this vector, and pi is the argument, this angle. Everything works fine. Any questions?
I'm just not sure that the graph is clear for me in that case.
What is clear?
That's not clear. Just about that. Why this -2 is the same like explanation. This.
Why -2 equals this?
No.
2 multiplied by -1, which is a cosine pi.
Yeah, no. The question is why we can draw it? Well, why not?
No, that's just what you were previously said about. And drawing the graph showing that the angle will be the pi.
Yeah, I didn't really prove that this angle is somehow connected with those angles, but in fact it is. I'm kind of showing it on the example, and in all the proofs should be in the lecture, I hope.
Okay.
So next, I have a more interesting exercise. Finally, something with both real part and imaginary part here. So what is, I wonder, the absolute value of this number? By definition, I have to take the real part squared and the imaginary part squared, like this. Then I get 1 plus 3. Square root of 3 squared is 3. Well, 1 plus 3, that's not hard. So as far as I know, that's 4, and the square root is 2. So this becomes 2 multiplied by the following. Okay, it's not. Thank you. It's nice to see your faces. So this becomes, well, this. And now I have to look at those values to see that they are cosines and sines. Okay, so they are cosine and sine of something. Once again, I ask you, what is this something? Who knows trigonometry from school?
This should be this pi 3 plus
Pi over 3?
no, because we have minus over 2, so it should be yes, it should be this exactly
2
this
pi divided by
Sorry, Arina, what?
pi
2
divided
pi divided by 3.
Okay, yeah,
not
Arina
pi divided by 3.
says 2 pi divided by 3, and
2
I
pi
think she is
divided by
more
3, yes.
correct.
Yes, I know.
Thank you.
I just was trying to remember.
Yeah, thank you both. So the idea is that we can again draw it on a unit circle, on a circle with length with radius 1, and so minus 1/2 plus square root of 3 over 2 looks like this. And so this angle, you can geometrically understand that it is 2 pi over 3. But I usually, when I have to do a task like this, I don't remember all of them by heart. I simply try to imagine a picture and understand what is the correct angle. But whatever way you find the more easy one, still the result is as follows. Everyone has to be able to do this. Okay. You have to be able to somehow from this find this, no matter which way you use. Do you memorize them by heart or do you somehow find out? But everyone needs to do this. That's life. So if you have problems, I ask you to refresh trigonometry for the next time. Sorry?
Please, could you explain the graph upper, just why we take point at -2?
The previous one?
Yes, yes. At the point at -2.
Well, because -2 is the number we are discussing.
Okay, that it means that our angle just went to the point -2 or what?
Yes. So our angle always is from this ray pointing to the positive direction of the real line, the best direction on this plane, and then from it we go in the positive direction, that is counterclockwise, and find the angle.
Okay. Okay, thank you.
Okay, now it works. So very good. So in this case, we get 2 pi over 3. So again, the original formula may be written as follows. Like this. And this is the trigonometric form of this number. Well, it's maybe not very nice, but still it works. And soon we're going to see how it works in an exercise. So, what is the next problem? I forgot. But before we go to this exercise, I have one more part, a slightly tricky one. Also, it has a misprint. Well, if you find the problem over there to the left, it has a misprint, but let's ignore it. The correct one should be like this. Okay. So I have the number cosine of alpha minus I sine of alpha. And I want to find the trigonometric form of this number. Please note, this is not the trigonometric form of this number, because it has a minus here and it should be a plus. We need to somehow do some magic to transform it so that this minus somehow becomes plus.
So maybe we should write to find the square from the sum cosine squared alpha plus sine alpha squared.
Yeah, indeed,
But this is
the sum of the squares of the coefficients is very easy to find. It is this, which we
one.
know it's 1. So nothing needs to be done here. But the interesting part is the angle. We get the following system. We want to find such an angle phi that its cosine is the same, but sine is different.
Is it possible?
P over 2 plus pk.
No. Alpha is unknown. It has to somehow participate in the result.
Pi plus alpha.
Pi plus alpha doesn't work because cosine will be minus cosine.
Minus.
Pi minus alpha.
Okay, pi minus alpha doesn't work because sines will be equal,
what
but
about P?
minus alpha, someone said, and it works. In fact, phi equals minus alpha plus 2 pi k, because of course I can add some copies of 2 pi if I need to. So cosine is an even function. Cosine of minus alpha is the same as cosine of alpha, and sine is an odd function. It changes the sign. So my original number equals cosine of minus alpha plus I sine of minus alpha. And now this is its trigonometric form. We will meet this number next time at some point, maybe. If I don't forget about it, we will meet. If there are any questions, do ask now. Otherwise, we shall go forward and begin multiplying numbers. Okay, no one is happy. I am happy because multiplying is fun. So consider please the following. Wait a second. Let me consult my notes. Yeah, that's right. The following. Wait, what? No, it's fine. The following. I'm sorry. Exercise. On one hand, we already know how to multiply complex numbers. We can do it by brute force, by opening the brackets and computing the result. Let's do it quickly. So the result is 1 minus square root of 3, because this by this, I times I is -1, so we get minus square root of 3, plus I times the following -1 and minus square root of 3. Okay. Let's look if this looks okay. So this isn't very hard to find. This particular question is easy to solve using algebraic form. I claim that in more complicated examples, it will be easier to use trigonometric form. Right now, it is not. Algebraic form is easy enough, but still, for like practice, I'm going to solve the same example using trigonometric form. Okay. To do this, first, I have to transform them into trigonometric form. Luckily, it's very easy to do so. For this number, I can extract the factor of square root of 2 outside. Then those numbers look like cosine and sine. I hope again that many of you remember those values. And for the other one, I extract 2 and I obtain this. Then I can write 2 square roots of 2 separately. And for this, I should well find what is the angle. So
3 pi divided by 4.
yeah, thank you. I was just going to say that I won't wait for you and write the answer because I want to save time, but thank you. You were faster than me. So, and this one is from the previous task. It is 2 pi over 3. So now the question is what happens next. And there is a general formula that was in the lecture that claims the following. That if we have two numbers in trigonometric form, and so we have two brackets like this, and multiply them, then the result is this. This formula can be checked. You simply open the brackets, you multiply, open the brackets, and find out what happens with the real part and what happens with the imaginary part. Using formulas from trigonometry, you will see that you obtain the cosine of sum and the sine of sum. But once you do this exercise one time, after that, you can memorize this formula. It doesn't really require memorizing. It simply says, add the angles. You memorize the rule that you add the angles, and everything becomes extremely easy. Instead of multiplying numbers, I add their angles like this. And what remains is, well, to actually add them. So this is 9 over 12, and this is 8 over 12. So together it is 17 over 12. Questions? So I solved the same problem with two methods. Again, this particular time algebraic method was much easier, but that will not always be the case. That's just a coincidence that this task was so easy that we were able to do it both methods. Please note that the answers we obtained look differently. Okay. Well, this answer is in algebraic form, and this answer is in trigonometric form. And it is kind of hard to transform one of them into another. It's kind of, if you are given this answer, if you are asked to make it into algebraic form, it will be hard because you need to find those cosine and sine, and vice versa. Vice versa is even more hard. The first one, if you are asked to find what are the cosine and sine, well, it's kind of complicated. They are not from the usual values. So, well, those are two different answers in, well, the two copies of the same answer in different forms. And so usually you pick the method depending on the next steps. Maybe in the next step, it will be also helpful to have trigonometric form, or vice versa. You have to be flexible. You have to like think, okay? I hope everything is understandable here. One final note is that we accidentally computed those cosines. This cosine, for example, equals 1 minus square root of 3 divided by 2 square roots of 2. Okay? If those two answers are the same thing, then automatically their real parts are equal. Thus, this cosine multiplied by 2 square roots of 2 equals this 1 minus square root of 3 that I have got here. Magic. Any questions? That's the next task. Okay. If there are no questions at the moment, then let me divide two numbers. Well, the same numbers, but now we not multiply them, but we divide them. Again, it can be done in algebraic form. We need to multiply by the conjugate, etc., etc., etc. That's not so easy. Again, it's kind of easy in this particular example, but generally it's not so easy. Instead, I'm going to use trigonometric form. So this is this. And this is this. And so when I multiply, the angles add. This automatically means, obviously, that when you divide, the angles subtract. So I need to separately divide those two numbers. That's not hard. And I need to subtract those two numbers. That's it. As far as I understand, the difference is pi over 12. So the advantage here is that this process is very easy. The disadvantage is, again, that the answer is in trigonometric form. That's not always nice. Sometimes that's not very good, but sometimes it's okay. It depends on the kind of things we're going to do with it next. Any questions about division?
So we just not sum, but we just subtract.
Subtract, yes. There is no S, no second S.
Then I think no questions.
Okay, no one? Then let me now do something, well, similar but different. I have a number And for the first example, let it be quite a simple number I, and I'm going to raise it to a power. Okay, why not? The only problem is that power is quite big. In this case, 77, for example. Well, the question is how to do this efficiently. I can multiply it by itself 76 times, but that takes time and I don't wish to spend it. So there are several approaches. There is a straightforward approach that works as follows. First, I compute several times. And the results are as follows. If you don't understand them, you can compute it yourself at some spare moment, but you can believe me right now, it's not important. It is important that the fourth power is 1. Then there is a principle you can use that you know from discrete mathematics. What can be done using this valuable fact?
77 divided by 4.
We can divide 77 by 4 and obtain with remainder and obtain that 77 splits into 76 and 1, and that this power is automatically 1 because 76 is divisible by 4 and each fourth power is simply 1. This is the same thing you have done with remainders in discrete mathematics. In fact, they're heavily connected, those topics, but unfortunately, that's out of our scope. Okay, this is a good and easy way we have done the task, but that's cheating. We have done the task because, well, like we tried and tried and tried and got 1 on the 4th attempt. What if this happened on like 24th attempt? Or what if it doesn't happen at all? That's a hard question. So lucky for us, the trigonometric form saves the day. Let us do the same exercise once more using the trigonometric form. The trigonometric form of I we have already discussed. It is cosine of pi over 2 plus I sine of pi over 2. So when I multiply those things 77 times, each time the angles add. So we get pi over 2 plus pi over 2 plus etc. plus pi over 2. That is, we know how to write adding a number 77 times. It is called multiply by 77. So the answer equals this. Wait, why by 12? Why don't you stop me when I write nonsense? Thinking. By 2. Now it's easy to see that 76 pi over 2 is 38 pi, and it doesn't matter. 38 pi is a multiple of 2 pi. It doesn't change the cosine and sine. So this equals cosine of pi over 2 plus I sine of pi over 2. Okay, that's it. So which way was easier? Well, hard to say. Both were kind of very easy because, again, the example is very easy. But I claim that if the number was not I, but something else, the second method has lots of advantages and lots of probability to be easier. And if there are questions to ask, otherwise we're going to see another example where this works.
Well, yes, the example is easy, but if trying to find this rule with the powers, then it's not actually happens. And to calculate 10 powers is a bit even more difficult and continue than just to use a trigonometric form, I think.
Yeah, kind of like this. If this coincidence doesn't happen fast, then we have troubles. So this trick doesn't require anything like that. And what I was talking about. Let me just note that this formula, so that cosine of phi plus I sine of phi to the nth power equals cosine of n phi plus I sine of n phi. On one hand, it's obvious. It is simply the straightforward corollary of the rule that you add angles when you multiply. But still, this formula has its own name. And the name is de Moivre's formula. Okay. Please note that in French, they don't pronounce the last letters of the word. So de Moivre, this E is not pronounced. And in Russian, that is formula Moivre. And I have no idea why there is no de, but there is none. Okay. Let me apply it to one more task. Let me compute 1 plus I to the nth power, where n is anything. Interesting question. Well, I have to transform this number into trigonometric form. That's easy. Indeed, 1 plus I, so if I extract square root of 2, then I get 1 over square root of 2 and 1 over square root of 2. That's cosine and sine of pi over 4. Okay. Like this. I draw a picture without x's so that they don't make too much noise on the picture. So now to find nth power, I can separately find nth power here and separately find it here. De Moivre's formula tells me that I need to consider n pi over 4 plus I sine of n pi over 4. That's it. That's the answer. Are there any questions right now? I'm going to discuss this for quite a bit of time. Okay, so let me do now the algebraic way by using binomial formula. This is a binomial, right? Sum of two things to the nth power. So this equals n over 0 by 1 to nth power plus n choose 1 times 1 n minus first power times I plus n choose 2 by 1 to this power by I squared plus etc. until n choose n times I to the nth power. Okay. Binomial formula, straightforwardly. You know it, right? It was in calculus. Okay, someone is okay. Nodding. Thank you.
Yes,
so
yes,
thank you.
One.
Then I can, well, I know the powers of I, they're easy. So I can rewrite this as follows. I'm sorry for writing too much of them, but let me stop here. And now in this form, it is hard to finish this, etc. Because what is at the end, it's hard to write because I to the power of n depends on n. So it is customary to simply write plus, etc. And it is obvious how it goes on. Okay. So now that I have this sum, I can split the real part and the imaginary part. The real part is this. And the imaginary part is I times this. So the algebraic way kind of fails because we have no idea how to compute those sums. You might think that, well, maybe there is some combinatorial way to find them. Maybe some of you know, for example, how to find the same sum if all the signs are not minus, plus, but if all of them are pluses. This is a much more easy task. However, so if, for example, it were pluses everywhere, then this can be done by combinatorics, by like simply thinking. But if there are minuses here, this is hard. It can be kind of done by elementary mathematics, but it's hard. So instead, we forget this idea. We use the polar form, the trigonometric form. And moreover, we obtained a wonderful, weird formula that this sum equals square root of 2 to the nth power times cosine of n pi over 4. This formula looks crazy. That's why I like it. Look, it has some integer numbers in the left-hand side, and in the right-hand side, it has square root of 2 and some cosine. That's crazy, but it works. This formula works. You can even easily check it for small values of n. Note that this number, again, it looks like it has square roots of 2, but in fact, it doesn't. Because if n is odd, then there is a square root of 2 here. But the cosine then also includes square root of 2. Okay? So they kind of cancel. Well, not cancel, but they give 2, etc., etc. So this number is in fact always integer. And again, it is for sometimes it is positive, sometimes it is negative, sometimes it is 0 for some values of n. Very interesting formula. I hope I have astonished you by this formula. At least that was my goal. But maybe some of you are not that easily impressed. Okay, that's fine. Still, well, I hope that at least I impressed some of you. And
I think it's really a good formula because just combining this binomial formula and the Moivre's formula, then we get that such a good result.
Yeah, that's really a miracle. And there are many things like this. There are ways to continue this to do more complicated formulas, but we won't touch them. Okay. If someone is interested, please look into a problem book like Kostrikin, and you will find many interesting tasks there on this topic. I really recommend it, but on free time, I mean, that's not required. Okay. If there are no questions, I will continue with another topic. I have a question. When do we start and when do we finish? 2:20?
20, yes.
Yes.
Okay, thank you. Thank you, everyone. Okay, at 20 minutes, so we have plenty of time. Don't worry, there is no quiz. I just have to check the previous one. But let me say that there is going to be a quiz on complex numbers at some point. Okay. So the next problem is an old problem. We have already discussed this problem. And we have solved it using a brute force approach by, well, it was very straightforward and very dull, and it worked for this particular equation, but we had like idea that if something was slightly different, we would fail. Today, trigonometric form will help us solve it again. And I claim that after we solve it again, the approach will be extended to many more problems of this sort. So, to solve a problem using trigonometric form, it makes sense to say that suppose Z has some trigonometric form. I don't know R and I don't know phi. Let's find out. Let's find them. If this is true, then, and if this equation is satisfied, this is the equation we try to solve. Then R cosine of phi plus I sine of phi cubed equals 1. This part is R cubed times cosine of 3 phi plus I sine of 3 phi. Okay. Once again, de Moivre's formula. On the other hand, 1 is 1 times cosine of 0 plus I sine of 0. So this number equals this number. Then automatically, their absolute values are the same. If you take the same number and compute its absolute value twice, you obtain the same result. And about the argument, we have to be more precise. But this equals this, and this equals this. Now I ask you how to simplify this. First, about R cubed equals 1. Can we say something about R?
It is 1.
R is 1 because R is, well, let me write cubic root of 1 equals 1, because R is real. For complex numbers, we don't know how to find such Z. Well, we do know for this particular equation, but let's pretend we don't know yet.
Yeah,
But
and
for
this
real
is,
numbers, we know.
but that will be a quite more difficult situation if we had a complex number here. Just
Yeah, but we can't have a complex number here because R is the absolute value.
I see. I just thinking about the set. Whereas I just always then remember this set with the square root of 1.
Yeah, we're going to see it in a moment. And so here, we now have to find what do those equations mean. We need to remember trigonometry once again. 3 phi and 0 have the same sign and the same cosine. What does it mean about 3 phi?
They are equal.
No.
Okay.
0 plus.
That's better.
2πk.
2 pi k. Okay, they might be not equal if they have the same cosine and sine, but if they are not equal, they differ by 2 pi k. And in all the previous problems, that was not important, right? We were writing plus 2 pi k because we are trying to be careful and write everything correctly, but it was not important. We immediately on the next step usually forgot about this 2 pi k. However, I claim that in this exercise, it is important. Indeed, let me divide this equation by 3. Okay, I have found 3 phi, I want to find phi. Well, dividing by 3 is easy. Here it is done. And now let me find which numbers correspond to those values of r and phi. Let me put k equals 0. Then r equals 1, phi equals 0. So z equals 1. Okay. Cosine of 0 plus I sine of 0, etc., etc. That's not very unexpected. But if k equals 1, then r is 1, phi is 2 pi over 3. So z is 1 times cosine of 2 pi over 3 plus I sine of 2 pi over 3. That is minus 1/2 plus square root of 3 over 2i. Okay. You might remember that last time I already had this as one of possible answers for this equation. Now we have obtained it by a different method. And so you see that it was important that I wrote this plus 2 pi k because it gives me different solutions. Magic. Moreover, I can then put in k equals 2. Then phi is 4 pi over 3. And that is, I will write the correct answer immediately. You can like spend a minute and find the cosine and sine, but I will immediately write it. So we obtain a third solution. And well, one may continue, but something more interesting happens. Now 6 pi over 3 is 2 pi. Which gives the same cosine and sine as the first one. So the argument is different, but the number is the same. And similarly, k equals 4.
So our answers will repeat.
Yes, so the answers will repeat, they will cycle. The next one is 6, equals 6 pi over 3 plus 2 pi over 3. So that is 2 pi plus 2 pi over 3. So it gives again the same z as one of the previous ones. And so on. If I consider more and more of different values of k, only 3 of them give different answers. And then the answers go in a cycle. Okay, clear? Everyone else? Okay. And so thus, we may consider not all k, but only k102. There are 3 of them because the root was the cubic root. The power was the third power. This idea may be generalized as follows. Oh, nowhere to write. This idea may be generalized by the following formula. That if z to the nth power equals 1, then z equals cosine of 2 pi over n, 2 pi k over n plus I sine of 2 pi k over n, where k runs from 0 to n minus 1. Okay. That's it. So this is the formula for the roots. We may now say that z is kind of the root of nth power of 1. And in usual numbers, a root was like a particular number, but unfortunately, as you already know from the lecture. Unfortunately, for complex numbers, it is hard to do it the same way. We kind of have to instead consider the root as a set of several numbers. That's not very convenient, but kind of people haven't haven't invented any better way. It kind of really doesn't exist for some reasons. So that's life. Unfortunately, the root now is not well, one number, but a set of numbers. Next time, we're going to discuss its properties for a moment. And we're going to discuss what happens if here we have not one, but another number. But I don't wish to talk about it too much today. Instead, let me consult my notes. Okay, this is fine. This is fine. In the other group, they asked me, well, what happens, for example, if here I have some number like 2? So let me have an example like this. Z cubed equals 2. Then Z is, well, cubic root of 2, which equals the following. I have to take the absolute value and take the cubic root and then take 2 pi k over 3. And this formula seems very silly. Does it? Well, I hope it does. Because it has this and this. It explains how to find the cubic root by using a cubic root. Is it stupid? Well, kind of, but not really. Because those are two different things with the same symbol. So it is stupid that people use the same symbol, but that's life, okay? Unfortunately, our ancestors decided to use the same symbol for those things. We can't really change the past. But this is a complex root of third power. So this is a set of 3 numbers. And this is the arithmetic root. The usual one from school. They are taken here from the same number, so that makes it confusing, unfortunately. I'm sorry, that's life. Still, it is easy to understand from the context which is the meaning here and here, okay? Unfortunately, again, the same symbol exists, so we have no other way than depend on the context and understand from the context what is meant here.
A tragedy of symbols.
Yes. Yes, that's it. So likewise, now we can replace 2 by something else, etc., but that part is the next time. Well, it's kind of silly that we have 10 minutes left, but I think that maybe we should stop. Otherwise, it will be not the same progress into groups and I will be confused. So if there are any questions to ask, otherwise, I think we have reached the end.
It just really, I just want to laugh because of this problem with these symbols. Sorry, but just that's the life, I know. That this is the same.
Okay.
It just,
yeah, this is kind of confusing, but that's life. We can't do anything with it. I'm sorry. I want to repeat, in the beginning, I said that, but not everyone was present, that your test results are going to be soon. Okay, tomorrow or the day after tomorrow. I don't have anything else to say, so if there are any further questions, if there are, sorry, no further questions, then let's meet next week. Yes,
Our
you-
homework will be soon.
Yeah, again, I missed the homework for the second time. It's becoming a tradition. I don't like that, but this weekend I have more time. So yes, I will prepare it soon. Yeah, last weekend was a huge problem for us because I had two tests simultaneously in different groups, and that was, I mean, in different programs, and that was kind of interesting. And now I have to check them simultaneously. But still, that's my problems. So
Just only stays to say I'm sorry for you.
yeah, don't worry, that happens. Well, that's because of those stupid 3 days that happened. Still, let me also say that again, repeat that the results are kind of good.
Yes,
Sorry,
that
sorry.
days are really stupid. You think that you can resort chill while all lectures are going, and in the real normal week, you understand that you have lost two lectures or seminars.
Well, I'm
So
sorry.
that's
Everyone tried to like say, as far as I know, explicitly that it is like not really free, but only.
yes, it's optional, but if you don't go, you will have a lot of problems.
Well, kinda. Yeah, I'm sorry. That's life. Again, yes. Officially, the choice was that you could like look at the recordings.
Okay, thanks a lot for
Mhm.
discussing.
Okay, so yes, I
Thanks a
hope there
lot.
will be a new home task today. And if there are no questions, let's meet next week.
Bye.
Bye.
Thank
Thank you very
you.
much. Bye.
Goodbye.